Hello, my name is Martin Walchshofer, and I'm working as a software developer at g.tec for almost 10 years. And today I'm going to show you the g.tec suite. First of all, I'm going to go through the g.tec suite a bit, which is our tool that packages all the research interfaces. And then I'm going to have some live demos to show you how you set up an experiment, how you can do some data acquisition in real time, data pre-processing, and how you can analyze data offline after you've recorded it. So as already mentioned, the g.tec suite is a software tool that packages a lot of research tools and applications, as well as development tools into one software, so you can start PCI research quickly. We have different tools. Some of them are using MATLAB because we use MATLAB a lot for prototyping and research. Some applications are standalone, and there are a lot of development tools for MATLAB, Python, C, C#, whatever programming language, so you can start research quickly. Some of the tools are licensed, and some of them are included in the g.tec suite. And in the g.tec suite, you can also check the software and hardware environment of the operating system, so we can ensure that you have all the tools required for the software. So first of all, when you start the g.tec suite, you have to download all the tools. The tools are automatically packaged and deployed within the g.tec suite. So you just have to click the download and update button, and you're informed in regular intervals about new updates. Then I'd like to go a bit through the applications available in the g.tec suite. So we have the g.esteemed, which is our functional electrical stimulator. You can use this hardware to simulate muscles. With the software application, you can control this simulator via an API. And we have the g.esteemed Pro, which is a similar device, but it's used for simulation within the brain. So with the functional electrical stimulator, you can simulate muscles. With the esteemed Pro, you can simulate within the brain electro grids, for instance. And if you want to stimulate electro grids with the g.esteemed Pro, you can combine it with the switching unit. Then we have the G recorder, which is basically a tool for visualizing data, recording data, and replaying data, which can be used, for instance, in the medical environment. Then we have a montage creator for different software modules. The montage usually means that we have these electrode caps or grids, and we have some software that defines where the electrodes are located on the cap or within the grid. So these are the standalone software modules, and we also have some MATLAB tools. For instance, the converter, which basically allows you to convert data from different file formats like PDF or EDF into formats that g.tec supports, like HDF5, for instance, or the other way around. And we have the montage creator as well there. And GBS Analyze is basically a tool to allows you to analyze the pre-recorded data offline. Then we have a couple of MATLAB applications. So you can combine MATLAB and the standalone application a bit. That's g.tec. We already have seen that in the previous talk a bit. g.tec is a tool for real-time data acquisition and signal processing. GBS Analyze is an offline tool where you can process your recorded data, and the montage creator can be used to combine it with electrode montage. The final sections are the development tools. We have a lot of different tools, so you can record data from g.tec amplifiers and stream it into your own applications or build applications on top of these tools or your research experiments. So we have a C API for all g.tec amplifiers, .NET API, Python, MATLAB, and if you want to use your own programming language, the protocols are described using the network API. For the Stimbox, we can present stimuli, like for instance, we can flash LEDs or present visual stimuli. We have C and Python API for this tool. And for the esteemed Pro switching unit, we also have an API. So this is a short overview about all the research tools we can provide at the moment. And within the g.tec suite, you're usually notified whenever new tools are available or there's an update available. So you can update your suite and stay updated with your research. And we have some licenses. So some tools are available without license, and some features are dongled, so they can be activated or deactivated. So by default, you need a license to use the g.tec suite. And if you just have the g.tec suite activated, then you can download the update and use some tools like the development tools. They don't have any license feature. Or you can visualize data using G-Recorder. But if you want to have more functions from the G-Recorder, you need the professional version. Then you can also check the ERPs, for instance, or replay data. Similar. With g.tec, it's similar. We have a basic version with some limited signal processing blocks and a professional version where you have all the tools that we developed so far. And GBS Analyze can only be used with a license. That's the user interface when you activate or deactivate your license tool. So you can do everything within the g.tec suite. And we have a diagnosis tool, so we can check your operating system, your hard and software environment, if everything fits our definitions. All right, and now we come to the practical part of my talk. So I'd like to show you how to set up a research experiment, how you achieve some data acquisition within HYSYS. So the first demo is going to be setting up a data acquisition and visualizing data in g.tec. The second demo will be how to add some pre-processing so we can process the EEG to look good. Then I'm going to add some data storage and some feature extraction in the next demo. And in the final demo, I'd like to acquire data, pre-process it, store it, extract some features, and stream data to another application. So that would be, this would be different research use cases where you could separate backend and frontend, stream data from one application to another. Later, I'm going to show you how to process the recorded data in GBS Analyze. And finally, I'd like to show you the G-Recorder, which is usually used in clinical environments, and how you could do some data acquisition within a clinical environment and run a research experiment in parallel. So therefore, I'd like to introduce my colleague, Michael Jordan, who is going to be my subject today. And I'm going to start with the HYSYS. Therefore, I've already opened MATLAB. So g.tec is a tool for real-time signal processing. And as you can see, we have a lot of different tools within HYSYS for data acquisition, signal processing, machine learning, and so on. But I'd like to show you how to set up an experiment from scratch. And therefore, I'm going to start a new Simulink model. While MATLAB is loading, I'm going to prepare my subject with the BCI. So I have a g.Nautilus here with dry gold pin electrodes. First I prepare the electrodes a bit, set up the cap. Okay, so the cap is set up. Now I'm going to align the gold pin electrodes a bit. In the meantime, MATLAB loaded Simulink interface. So Simulink is basically a drag and drop editor where you have functional blocks that you can connect to each other. And we have a library in here, which is called g.tec. And first of all, we want to acquire data from the PCI that I set up on Michael, my colleague. So therefore, we drag the amplifier block into the model. We have to turn on the BCI. And then we can check if we can already find the BCI. So the g.Nautilus is already found. So we can open it. And configure the device. So I've used the dry electrode system. Therefore, I'm going to set the input range of 2250 millivolts. And that's basically everything you need to know to set up a data acquisition. This model should already run. I let it run for infinite amount of time. But to make it a bit more useful, I'm going to add some data visualization. Therefore, I'm adding the scope into the model. If we now connect that one, we've set up a basic data visualization model. If I click run now, we hopefully can see some data floating in. Yeah. So right now, data is acquired and we can see data floating in. Where is the scope? Hidden. Restart the model. Here's the scope. Drag it to the correct screen, and we can see data is floating around. But it's not much useful data yet because we didn't apply any pre-processing. So data is just floating around randomly. The next demo I'd like to show you is how to add some pre-processing. Therefore, I'm going to stop the model again, and I'd like to apply some filters. So for the filters, we have the pre-processing toolbox. So we have a lot of different filters in here, but for default EEG pre-processing, I'd like to add some notch filters. So a notch filter usually removes a specific frequency band, and we have a power line hum in Europe with a frequency of 50 Hertz. So I'd like to remove that one because that's an artifact that we don't want to have in our signal. If you're in the US, you would do the same, just with a frequency band of 60 Hertz. I'm going to add this block as well. So this model would run in US and in Europe. And usually our PCI frequency range for surface EEG, especially with dry electrodes, is within 1 to 30 Hertz. So therefore, I'm going to set the bandpass with a cutoff frequency of 30 Hertz and a high pass cutoff frequency, say from 2 Hertz for dry EEG. And that's it. So now I can show you the difference with and without of the data with and without pre-processing. So we have two scopes in here now. One is showing pre-processed data and one is showing raw data. So this is our raw data scope. And on the other hand, we have our pre-processed data scope. Yeah. So we set it to a useful EG frequency range, amplitude range of minus to 100 microvolts. And we can already see some good EG. And on the other side, you can see how the signals would look like without any pre-processing. So it's just floating around. Now we can do some simple EEG signal quality tests, like you can blink your eyes a couple of times. You can see, especially on the electrodes close to the eyes, you can see some big blinking artifacts. You can clench your teeth a couple of times. Now we can see some muscle artifacts in the EEG signal, and you can close your eyes for about 10 seconds. Now we can see alpha waves when the visual cortex synchronizes, and we can see, especially on the visual lobe of the brain, we can see some alpha waves. So that's good. We can also inspect the frequency spectrum for all the channels that we're acquiring, and maybe just look until frequency range of 50 Hertz. So you can close your eyes again. And we can see the 10 Hertz peak is perfectly visible in the EEG frequency spectrum. That's cool. Within 10 minutes, we set up the data acquisition system. We applied some pre-processing filters and are running a BCI experiment already. Typically for research use cases, you want to add some feature extraction. So mostly you're not looking at the raw EEG or processed EEG. You would add some band power features, for instance. We also have some tools for this use case. So in our library, we have some feature extraction libraries as well. So in this case, I'd like to add a band power node. And I'd just like to check the band power for different frequency bands for one single channel. Therefore, I'm going to split the 8 channels from the PCI and just look at one channel. Now I'm splitting up the 8 channels from the BCI without any programming, just using the drag and drop editor, and I'm going to feed that into the band power node. And within the band power node, I can specify which frequency band I'd like to look at. So I'm going to calculate some delta, theta, alpha, and beta frequency bands, and I'm going to set that up appropriately now. So delta would be around 1 or 2 to 4 hertz. I have to set the system to 250 hertz beforehand. So our PCI is recording with 250 hertz, and we have to tell that to the model. Now I can set up the block. So delta would be 1 to around 4 hertz. Line. Forgot to apply correctly. Delta would be 1 to 4 hertz. Take a window size of a second. Then I'm going to add the theta band, the alpha band, and the beta band. So I'm going to set the frequency ranges accordingly. Like theta would be around 4 to 8 hertz. Alpha would be around 8 to 12 hertz. And beta would be around 12 to 30 hertz. And now I've added some feature extraction for band power features to the model. I'm going to sum the signal up and going to display it in another scope so we can follow what changed. So in the next scope, we would see from one of the back channels, delta, theta, alpha, and beta, and we're going to display this in another scope. So this is the whole model right now. You can see from the amplifier node, we're feeding raw data in the first scope, pre-processed data into the second scope, and some feature extraction into the third scope. And again, we can run the system now and check what changed. So in the first scope, you still see raw data that is just floating around. In the second scope, we can see pre-processed data and frequency analysis. In the third scope, we can see some band power features. Let's try to fit all of that to the screen. The first scope still floating around. In the second scope, we can see some good EG. And in the third scope, we can see some frequency bands. So if my colleague would close his eyes for around 10 seconds, we can see that the third channel had a big rise because he closed his eyes and the alpha band was rising. So right now it's again closing his eyes, alpha is rising, he opened the eyes again and alpha was falling again. So that's basically already a very simple PCI model with frequency band analysis. So that's often used in neurofeedback applications, for instance. And I mentioned before that I want to add 2 more things to the system. Like the next thing I'd like to add would be some data recording. Therefore, I check the library again. There's some data stream blocks as well. So usually for BCI systems, we want to record raw data so we are able to process them offline after the experiment as well. Therefore, I'm going to add the raw data logging to the very beginning of the model, just naming the file as default. And we can run the system again. All right, system is running, and we can see that the file was created. And now we are running some data storage, raw data visualization, pre-processed data visualization, and some feature extraction in parallel. And we were able to set the whole system up within 15 minutes without any programming required. So that's pretty cool. And the final thing I'd like to show you is how to get data out of Simulink and acquire it in your own application, for instance. So you could easily prototype your backend and data processing and so on within HYSYS and add some front end or GUI in some other application. Therefore, I'm going to add a lab streaming layer interface. So in the HYSYS toolbox, there's also a lab streaming layer interface. And we're having 8 channels that I want to stream into another application. We just need to name the stream, name it raw data, and it's EEG, and our sampling rate is 250 Hertz. So now we have an interface to some external application, and I'm going to add that to the filtered or raw data. I named it raw data, so I'm going to add it to the raw data stream. All right. And again, I can run the system. Now we're recording data, visualizing raw data, sending the raw data via lab streaming layer, visualizing some pre-processed data, and calculating some band power features in parallel. And to show you how you would receive data in your own application, I created a very simple console application for lab streaming layer. So this one is just looking for data streams. And if I find a data stream, I print it to the console, but you could create a nice looking GUI with some scopes or whatever you want. I can already see the stream name that I named before, the raw data stream, and can receive data from 8 channels that I'm sending from Simulink to my own application. So this would be a common use case to separate backend and front end to create some nice looking GUI, but doing all the hard work and research stuff in HYSYS, for instance. All right. So this demo showed how to do some data acquisition, to add some pre-processing, data storage, display, feature extraction, and streaming all of that. So the next thing I'd like to show you is how you could record data with HYSYS or G.Recorder, for instance, and load it into GBS Analyze, which is our offline processing toolbox. So if you installed the g.tec suite, you will find GBS Analyze within your MATLAB tools, and you can either open it from MATLAB or from the g.tec suite. And that's the user interface of GBS Analyze. And first, I'd like to load the data that we've just recorded. So here we have the data file from the recording before. And I'd like to open that one. Now we have 9 channels. Our PCI has just 8 channels, and the first channel is some timestamp. The first thing I'd like to do is to remove the first channel because we don't need the timestamp channel. Therefore, I'm going to select the channels that we're going to use, the channel 2 to 8 and 2 to 9, and only include that into our processing. So I'm asked if I really want to remove that. Fine. Now we have 8 channels, and we recorded raw data. That's why we don't see much data yet. So the next thing I'd like to do is to show you how you can add some filters to the data. And therefore, I'm going to design a filter. I'm going to design a Butterworth filter with a filter order, say 3. I've recorded with dry electrodes, therefore I take a lower cutoff frequency of 1 to 2 hertz, let's take 2 hertz, and an upper cutoff frequency of 30 hertz, because that's where most of the EEG or the signals we'd like to use in BCI experiments located. And I name this filter reprocess. Bring it to the list. Okay. And now I have to select that's a typo. Now I have to select which channels I'd like to apply the filter to. So I'm going to include channel 1 to 8 and preprocess data. Now we can already see that some filters have been applied, but in the beginning of the file, we just have filter swinging. So I'm going to remove the first 10 seconds from this file. So first 10 seconds with 250 hertz would be 2,500 samples. And I'm going to remove the data. Now we can already see that the signal is flatlined, so we have to scale it to some range that is useful. Therefore, I'll take the scaling feature and scale channel 1 to 8 to plus minus 100 microvolts, where we would expect good EEG to be. So we can already see the EEG, and we have one channel with a bit more artifacts because we didn't apply any notch filter yet. Therefore, I'm going to add a notch filter as well. So there's already predefined 50 hertz notch filter. Going to apply it for channel 1 to 8. And now this one channel also looks clean. So it looks like we have some good EEG. And we can also apply some signal quality checks to see if we have good channels or not. We're going to apply that for channel 1 to 8 again. And it tells us we would have had 1 bad channel or 2 bad channels, and the other ones were well. So that's how you can, and I'll show you how to record the data, to load it, pre-process it, and check if the data is useful or not. So for your PCI experiment, you would maybe remove this channel or apply some advanced machine cleaning algorithms like Oscar or ICA or similar algorithms, so you can also get data from these channels. All right. Now I've been through the first 2 real-time applications, and the last use case I'd like to show you is how to record data using g.recorder. That's what a lot of people do in clinical environments because it's not a research tool as g.tec, where you are aligning blocks. Everything is compiled and then it's an application. But you can also record with this application and run PCI research experiments in parallel. That's what you sometimes want to do in clinical environments. So I'm going to close my previous application. And I'm opening g.recorder. The g.recorder is one of the applications in the g.tec suite. There's g.recorder. And I'm going to connect to my device in g.recorder and configure it. And as mentioned before, g.recorder is a software for visualizing data and for recording data. So first, I'd like to show you how to visualize data. Like before, we can see the raw EEG without any processing filters applied. So it's floating around like this. And also in g.recorder, you can apply some filters, some visualization filters. So we could apply some filters in here, like 50 Hertz notch filter is already applied to the first channel, to the second channel, and some useful PCI filters. So now we would see channel 2 is within the expected frequency range for EEG. Plus minus 100 microvolts. And I'd like to show you how you stream data from, now we're calculating CZ minus CZ. That's not useful. We have to remove the bipolar channel, so it becomes useful again. The data is loading in here. And we can see some good EEG on channel 2, and the other channels actually don't look that bad, but they're just floating around. So this is the channel we applied filters to. It's within plus minus 100 microvolts, and that's good EEG. So if you can close your eyes again, Michael, you should see some alpha waves again. And open it again. Yes. And now I'd like to show you, like that's what you would do in a clinical environment. You could pre-process your EEG maybe, and then you could record data. So you just click record, name your file, and data is stored to your disk, similar to the application in HiSys, but you don't need any research tools, and you don't have to know much about signal processing to control g.recorder. And now the use case would be that you're in a clinical environment, you're running your data acquisition in g.recorder, and you want to process data within a research tool to run your research experiment in parallel. And therefore, we could go to g.tec again and just leave the data acquisition running in g.recorder. I'm creating a new model. And I'd like to add some data visualization again. So in g.tec, there's a node called remote data acquisition. That means that multiple applications within your network can share the data stream. So you can run your data acquisition in G-Recorder. Like if you're doing some sleep analysis, you can run the data acquisition in G-Recorder, and you're doing some frequency band analysis again in g.tec. Then you can share the data using the remote data acquisition. Start the data acquisition again. And now we can check again within g.tec if we can find the data stream. So that we can find the data stream. It's called g.nautilus, and it's already opened. So the software checks that the data is already acquired by some external application. So you cannot reconfigure the system, but you can get the data from G-Recorder. And the next thing I'd like to do is again to add some data visualization. So I'm adding some scope again to the data stream that we are recording in an external application. And I want to run that for as long as I want. All right. And we can already see data coming in our research application and in our compiled application. So I can show it in parallel. On the left-hand side, we have the data in G-Recorder with some pre-processed channel 2. And in g.tec, we are acquiring raw data right now. And now we could, again, do some pre-processing in g.tec. So we can look at some more specific features that would be interesting for our research use case, for instance. So again, I would go to the g.tec library, and I'd like to apply some pre-processing filters. Therefore, I'd add some Butterworth filters again for notch and for bandpass. And like before, I'm adding a 250 Hertz filter for the 50 Hertz frequency band as a first stage filter. Second stage filter would be 60 Hertz filter, also for 250 Hertz. And some bandpass filter. Beforehand, we used 1 to or 2 to 30 Hertz. We can do the same again. And in HISys, we don't need to do any programming. We just connect the different processing stages, and we can quickly set up some signal processing chain. And I also want to visualize the second data stream. So right now on the bottom right, we see the raw data stream. On the top right, on the bottom right, we see the process data stream. And on the left-hand side, we can see the data still being recorded in G-Recorder. So raw data stream actually looks good, but we can easily disturb it. Like if I'm going close, you can see the frequency band, some noise being introduced, and on the bottom, the signal looks pretty clean. So we can still check if there's still EG in the signal. So can you blink your eyes a couple of times? You can see some very nice eye blinks. You can clench your eyes, teeth a couple of times. We can see some EMG artifacts in raw data, in process data, and you can close your eyes for 10 seconds. And we can see some alpha waves appearing in the stream data. So that's pretty cool. Within a couple of minutes, we set up our research experiment again in parallel to some clinical data recording. And I think I'm running out of time, so that's why I come to an end for my presentation. I hope you got some idea what you can do within the g.tec suite and how easy it is to set up data, to set up some signal processing, record, process data, and stream data.
Thank you very much, Martin and MG. There's a question from Manuel. Can you use g.tec also in embedded real-time applications?
Yeah, I mean, it's possible to split backend and frontend with g.tec. I mean, you cannot export the model to some C code or something like that, but you can create your models in g.tec and stream data to another application. Do you mean embedded in terms of microprocessor? I think not right now with our toolbox.
Thank you very much. Then Martin is asking, is it possible to stream the data of two unicorn devices at the same time?
Yeah, should be possible. Like the Bluetooth interface is a bit limited, so I've tested two devices already. Sometimes with three, the Bluetooth is overwhelmed already. But in worst case, you can always stream on many PCs in parallel, like on 5 PCs. You connect one unicorn to each PC and then take lab streaming layer and merge all the data streams. So that would be one solution for multiple PCs. And on one PC, I wouldn't do more than two devices because Bluetooth is breaking at some point.
And somebody's asking, how can you combine a virtual reality device from Meta with EG data from g.tec?
From g.tec, you'd need, at the moment, you'd need a PC in the system, and you can stream data with some network interface like UDP, TCP, or lab streaming layer. So you need the PC as a data acquisition system. Then you could stream data in real time to the Meta Quest if it's in the same network. And I don't know, if you're running a paradigm in the Meta Quest, you could align the trigger in there, and then you would have a PCI system.
And Ali is asking, when you're using a higher cutoff frequency of 30 Hertz, why is it still necessary to use a 50 Hertz notch filter?
The low pass filter is not perfectly steep, so it's just dampening, and the 50 Hertz are that big that you can still see it in some cases. So you can go for higher filter orders, but then you would at some point get unstable filters or filter swinging, or you additionally add another 50 Hertz notch. With dry electrodes, even you sometimes see the 100 Hertz notch and multiple frequencies still if applying a low pass filter.
Ushman is asking, how do you see the usage of capacitive EEG electrodes? Because then you don't need the galvanic connection. Could this be more feasible?
I'm not an expert in this case, so maybe I can hand over to you, Christoph.
So up to now, these capacitive EEG sensors are pretty big, and they have, of course, the problem that you get a lot of interference from things in the surrounding. And this is with electrodes which are in close contact with the brain via the electrode gel much better to handle. So this interference is a big problem, and nowadays also we're still the size of these capacitive sensors. But this could improve, but the shielding must be improved much more. Then there's a question if there's an SDK for G recorders so that you can put in custom-made hardware.
Like streaming in is not possible, like it's not an open framework or something like that, but you can stream data out, like you can record from GUSBM, G-Nautilus, G-High-Amp in G recorder, and then you can use the G-Need Access API and stream data into your own application.
The manual is suggesting Tomek to come to France because they're very good cosmetic and perfume makers, and he could test his brain computer interface technology over there. That's a very nice idea. And Ben is asking if g.tec is part of national and international research projects. Yes, we are active at the moment in about 15 international research projects with about 100 partners, and we participate all the time. So this is mostly in Europe, USA, and Japan, but of course we work also together with other universities. Then Sandu is asking or saying he spoke with the professor about the 14 credits that we give out for the spring school for 140 lectures. So everybody will get a certificate who participates in the 140 lectures, and you can hand it in at your university, and then you can also attend the exam. So you will also get a certificate for the exam, and both together should be handed in at your university, and then you can discuss if you get ECTS credits for the spring school. Many universities already accepted. And maybe you can just show this material already to your professor to check it out. And with that, I would actually like to thank MJ and Martin again for the very nice lecture. Thank you very much and enjoy lunch.